Hi there, and welcome to Raylene Math. We're going to look at sequences and see how they're connected to functions. Have you ever had that feeling in math class where you've seen this stuff before but you can't quite place it? Or have you ever had the feeling in math class where you've never seen this stuff before? Well, really a lot of math is connected. And if we can see how it's connected, then we can use what we already learned and understood to move forward. In the case of sequences, which is a list of numbers, a list of terms, we often don't represent the sequences as a table of values. We might have a sequence 1, 1 over 2, 1 over 3, 1 over 4. And because we don't have a set of inputs and outputs, it's kind of hard to know what these values represent. Are they the inputs or are they the outputs? If we were to represent the values corresponding to some kind of input, this is the first term, this is the second term, and so on, we would be able to see the inputs of 1, 2, 3, 4, etc., and maybe call those inputs n, and see the outputs as the value of the nth term, or the function output for the input of n. And we can see that the outputs are actually these values 1, 1/2, 1/3, etc. The reason we don't always need to write the inputs here then is because it is implied or built in to the ordering of the numbers in the list, in the sequence. However, we can connect this to what we've already done before in a pre-calculus and algebra class where we have x and y is the output of a function x, f of x. The only difference is x is not constrained to being these positive integer values the way that n is, because we have n, which is a member of the integers or the natural number set. Meanwhile, the x value is a real variable, and the only restriction on x might be coming from the function. So in this particular case, let's take a look at the function, the reciprocal function. And first of all, when we're talking about the values of x and n, we have to realize that x has any restriction depending on the function, but in general it's coming from this set of real numbers. So again, x is contained in the real number set, and n is contained in a subset of the real numbers, namely the integers, and in most cases we tend even to take n to be contained in the natural numbers or the counting numbers. Meanwhile, y and a sub n are the outputs of a function, and so y is also contained in the reals, and it might be easy to think that an, the output, has to also belong to the integers, but it doesn't. For example, if we consider the function f of x to be the reciprocal function, so f is the reciprocation or 1 over or raising to the exponent of -1, we know that even if we started off with inputs that are whole numbers, that the outputs are not also whole numbers or integers. So the an does not also have to be an integer like the input is. So an can be any real number as well, depending on what the function is and how the function changes the input. So if we have f is the reciprocal function, we might need to specify some x coordinates and some y coordinates. It's not automatically assumed to start at 1 and to increase by 1. We could have negative x values, we could have decimal values, we can have fraction values, whole numbers, and irrational values. And the y coordinates will adjust. So let's take a look at this graph briefly. We're going to sketch them just to see how the function and the sequence values are connected. Here in Desmos, we can see the sequence of 1 over n, and we can see the function of 1 over x. The difference between the blue sequence and the red function is that for the red function, all of the x values except for 0 are part of the domain of the function, and we have an infinite number of values on the graph for x and for y. We also have an infinite number of values for the sequence. We just don't have all the values in between 1 and 2, 2 and 3, 3 and 4, etc. However, because n is a subset of the domain of x, we see that there are consistent values. And it's in this way that the sequence and the function are connected, because there are ordered pairs that are the same for the blue sequence as there are for the red graph for the continuous function. Okay, so the next thing we want to do is take a look at a linear function and an exponential function by modeling. So we're going to have 2 points, 1, 2 and 2, 6. And actually it'll be really nice to look at this in Desmos. So if we just take the sequence now, we're going to delete a whole bunch of values, input a new table, and we're going to have a sequence of 1, 2, and 2, 6. It's not so much a sequence as just plotting points. And we want to come up with a line that goes through those 2 points. So there's lots of ways to do it. But one of the ways that I want to do it that is consistent for all functions, whether it's linear or exponential, is not to take advantage of a slope definition or any other special case information. Rather, we're going to take a look at a general model for a linear function, which is y equals ax plus b. You could also call it ax plus by is equal to c, but I think here we only have the two parameters a and b, and it's easier to work with this version. So we need two equations to solve for the two unknowns a and b, and we have those from the points. So the first time through we substitute point a, and we're going to get that 2 for y is equal to a times 1, which is a, plus b. And the second point, when we substitute for b, we are going to get that 6 for y is equal to 2 times a plus b. And now we're going to solve the system of simultaneous equations by eliminating the b. We can do that by taking equation 2, subtracting equation 1, and 6 minus 2 is 4, 2a minus a is a, and b minus b is b. So we end up with a equal to 4, and we can back substitute that value into either equation 1 or 2. I'm going to do it into equation 1, and then we'll get that 2 is equal to 4 plus b, and therefore b is equal to negative 2. So we have the values for a and b, and so now we have our linear equation, which is y equals 4x minus 2. So we can see that we have a y-intercept of negative 2 and a slope of 4. And if we had calculated slope using the slope formula, the rule, we would have gotten the same thing and solving for b, or using point slope form. There's multiple ways. Let's just plot that equation and confirm that it indeed goes through the 2 points we plotted. Y equals 4x minus 2, and it does go through the 2 points. Now we also want to come up with an exponential function, but coming up with an exponential function requires us to know the exponential model to start with. So now we're going to start off with y equals a times b to the x plus c, and we notice that we've got 3 parameters, a, b, and c. And it seems fairly likely that we want to have a horizontal asymptote for this exponential function of the x-axis, so we are going to make an assumption or a choice to put the horizontal asymptote at y equal to 0. So now we're still solving for 2 unknowns, a and b, and we can repeat the process that we did in part A in a very general approach that is not specific to being a linear or exponential function. So if we substitute the first point, 1 for x and 2 for y, we get that 2 is equal to a times b to the 1, or simply ab is equal to 2. And the second point gives a second equation, namely that 6 is equal to a times b squared. Now we are going to eliminate a this time, but we are going to do so by division. So we're going to take equation 2 divided by equation 1, and the left sides divide to give 6 divided by 2, which is 3. And the right side of equation 2 divided by the right side of equation 1 is going to reduce the a's, and b squared over b reduces to b. So from this we can back substitute now, and I'm going to choose to do so in equation 1, which says that 2 is equal to a times the b value of 3, and therefore a is equal to 2/3. So we have our 2 parameters for our exponential model with a horizontal asymptote at y equal to 0, and therefore y is equal to, let me just put exponential equation, and we're going to get y is a 2/3 times the base of the exponent 3 raised to the x. So if we take a look now at our graph, we can come up with an exponential model y equals 3 over 2 times 3 raised to the exponent of x. And let's just check to see if we had a mistake here. I think the a value is 2/3, wasn't it? Yeah. So we go back and just rewrite that. 2 over 3. And we see that we indeed have the exponential function going through those 2 points. So from this perspective, we have an exponential and a linear function requiring 2 points to go through the graph. Now, why am I picking on these 2 functions? I want to explore them a little bit as linear as continuous functions and then connect them to sequences. We saw we had a slope and a y-intercept, y equals mx plus b. So m represents the slope or the gradient or the rise over the run. If we have a line, we can make a right triangle out of 2 points on the line, and the height over the base, altitude over base, is going to be the slope. By the way, this is also the same as the opposite over the adjacent to the angle theta, and so to connect even further, the slope is the same as the tangent of the angle of inclination. But I'm getting off topic here. We also see that the y-intercept is the value for b, and it's nothing more than the y value when the x-coordinate on the graph is 0. There are no restrictions on these values, so m and b can be any real numbers. I suppose the only problem is that they can't be undefined, which means they can't be infinite or fail to be a real value. Furthermore, number 12, we want to discuss the b, x, and y coming from the statement y equals b to the x. In this statement, we have that the base of the exponent is equal to b, the exponent itself is equal to x, and the power, which is the output of the base raised to the exponent, is called y. We do have restrictions here, and for a continuous function, we can't have a negative base, and if we want there to actually be exponential growth or decay, the base can't be 0 or it can't be 1. So not equal to negative, not equal to 0, and not equal to 1. The reason is if we have 0 to the x, then we have a horizontal line, y equals 0. Similarly for 1 to the x. And a negative base is a problem because if I take negative 2 and raise it to a real variable x, which is, say, 1/2, then we're talking about the square root of negative 2, which is not a real value. And so we want to ensure that we are working within the real number system for both x and y in the real plane. So the base values can be contained from 0 to 1, union from 1 to infinity. And in fact, this gives us decay from 0 to 1, or a base value from 1 to infinity gives us growth. But we just saw an example of a sequence an that allowed for a base to be negative. So we're starting to see that the fact that x is contained in the reals, but n is contained in the natural numbers, or at least the integers, is changing the characteristics of the graphs, and not all sequence graphs can be represented by a continuous function. Well, moving on, the exponents can be any real value. There's no restriction on what number you can raise a base to, as long as the base has these characteristics. And then the power is going to be a positive number, in a sense repeatedly multiplied by itself the exponent number of times, and so positive times positive times positive, any number of times, is still going to be positive. So y is going to be a positive number, which means greater than 0.